My name is Dimo. This is my project see-through-video, temporal consistent underwater video distortion. When objects and scenes are submerged underwater, the perceived color and other visual effects are largely different from when they are viewed on the surface. This poses challenges to underwater photography and videography, as the color red goes away quickly when the footage is taken in deeper water, along with effects like backscatter. We can directly describe the underwater floor model as the direct signal component and backscatter component. And generally speaking, the underwater distortion problem is an inverse problem of its floor model. The subscript C stands for the color channel R, G, and B. I on the left is the picture taken on the water. J is the image we want to recover. There's an exponential term multiplied onto J, which is attenuation onto that particular color channel. And then there's the additive term on the right, describing the backscatter effects. This model is being adapted in various ways in various work that employs different methods. Many work has been done in the field of underwater image distortion. See-through is a parameter optimization-based method that solves the explicit coefficients of the proposed water floor model in a given image. In single-step latent diffusion for underwater image distortion, they proposed a method that uses a similar floor model to generate a large synthetic dataset from the air scenes and produce backscatter and illumination estimations. However, their relationship to the clear image is very implicit in the neural network, which makes it harder to interpret and very difficult to retrain. Most of these works focus on single image distortion. Naively process each frame of the video independently will cause flickering effects from temporal inconsistency. To solve this issue, I took inspiration from deep video prior to use a neural network to approximate a smooth image distortion operator, which we'll talk about in depth later. In this work, I developed a temporal consistent underwater video distortion pipeline based on the idea of see-through and DVP, which I call see-through-video. Here's an overview of the pipeline. Starting from underwater video that we want to recover, it first feeds into the depth estimation module shown in gray. And both the underwater footage and the depth map for each frame is feeding to the see-through algorithm to recover the coefficient in the floor model, which produced a per-frame distortion of the raw clear images. And finally, we feed the per-frame distortion video from see-through and underwater raw footage into DVP module to produce a temporally consistent final distortion video. In the original see-through paper, they used the structure from motion or SFM method to get depth D. However, SFM only produces relative depth, but see-through would require absolute metric depth to work, so they had to have objects with known scale to recover the absolute depth. In see-through video, I utilized the Apple Depth Pro depth estimation model to directly estimate absolute metric depth from images. Sometimes Depth Pro would output depth estimation that's unbounded, for example 100 meters in open water, which poses challenge numerically when feeding to the downstream see-through framework. Thus, the depth estimation is post-processed first by collapsing unbounded estimations to a preset deepest depth. Also, when testing various videos and images from my own dataset, I realized that for some extreme footages, the depth estimation can output hallucinated artifacts, as shown on the screen. There's like weird L shape and like this rectangular-ish artifacts that hallucinated from the model. This is mitigated by merging a blurred version of the depth map, weighted by per pixel confidence score, which is calculated by the variance of its local region. Depth Pro only processes frame one by one without considering it being a video. So in this step, I basically employ a simple two-pass expansion moving average, or EMA, to inject temporal consistency or smoothness, at least, for depth map. By 2-pass, I mean I average results from a forward-pass EMA and the results from a backward EMA to reduce time delay compared to only use a forward-pass. This is possible because the information is not coming online one by one. We have the full video. The left depth map is the raw and the right one is EMA. You can see it's a lot smoother. The original see-through implementation fits parameters per frame, and it's quite expensive. We can realize there are several parameters that are independent of the view of the video, such as B infinity, which is backscatter and infinity, and beta B, which is the backscatter attenuation. They are property of the water in the video and should be coherent throughout. Using this assumption, I was able to do uniform sampling across the video to calculate these parameters and using average for the rest of the frames. This shared parameter method boosted the processing speed by orders of magnitude and helped with the flickering effect in the scene with rapid camera movements. The left being the raw see-through coefficient optimization per frame, and the right uses the average coefficient for the rest of the frame. We can see the flickering effect being largely reduced, but for some parts of the video, you can see the colorization is not entirely correct. I took inspiration from the original deep video prior paper and implemented my own version. The idea of a DVP is that if we have an image processing algorithm, in this case is see-through processing, that has no temporal awareness and it can be described as some function f, where f is the operator that restores some input image I. It will produce a flickering video if we just apply f to each frame. And the idea is that we can learn a operator G parameterized by some neural network to learn directly on the test video to approximate the operator F. Here, the network is parameterized using a CNN UNet, which is a autoencoder architecture. So hopefully it not only learns the pixel level temporal smoothness, but also semantic level temporal smoothness. Further, the reason why it's smooth is neural networks are inherently smooth because their Lipschitz is continuous. In my experiment, DVP works actually very, very well. Not only it works well on the average version of the parameter, which has less flickering, but it also works very well on the version of the video that has basically no deflickering. There are also a few limitations. For example, when I test my video with almost zero red channel content, there's no way of distortion. This is because unlike generative models, see-through does not have a prior that trained from a larger data set. Also, the performance of the pipeline can be further improved for higher resolution and higher frame rate videos. And there are also cases where I see bad distortion when having images such as looking at the sun and stuff like that. But this issue can be mitigated by further fine-tunings and smart modeling of the parameters in edge cases. Hopefully I can continuously improve this work and make it better. Thanks.